Hello students, welcome to Shri classes. Part B, Human Eye and Colorful World. In that part B pertains to colorful world, atmospheric refraction. Today we will see atmospheric refraction and also certain natural phenomena that are explained by atmospheric refraction. Those are apparent star position, which is different from the actual star position, and twinkling of stars. Why do stars twinkle but not planets? Advanced sunrise and delayed sunset. So these phenomena we'll see due to atmospheric refraction. See, one important thing you should know before we study over here. What is this Earth's atmosphere basically? See, air is a homogeneous mixture, but atmosphere is not a homogeneous mixture. Earth's atmosphere contains dust particles, air molecules, water droplets, smoke particles, etc. So Earth's atmosphere is a heterogeneous mixture, first of all. And when there is a heterogeneous mixture, and not only that, it is Earth's atmosphere is a heterogeneous mixture, first of all these particles. And also, what about the temperature of the Earth's atmosphere? Earth's atmosphere temperature cannot remain constant throughout the atmosphere. The atmosphere near the Earth's surface gets heated up. It is warmer compared to the atmosphere above it. And therefore, the density of the different layers of the atmosphere continuously change, and the temperature also changes. And hence I will say, when I say the density here, it is optical density also. So Earth's atmosphere's optical density is not constant throughout the atmosphere due to change in its density and the temperature. That means it has a continuously changing refractive index. So that should be kept in mind before we study. So that means Earth's atmosphere has a continuously changing refractive index. It is not constant. How does it vary? Just see here. Refractive index of the Earth's atmosphere increases from top to bottom. That means towards the surface of the Earth, from the sky, if you compare the Earth's refractive index, the refractive index of the Earth's atmosphere increases towards the Earth's surface. That should be kept in mind. Fine. What is atmospheric refraction? Change in direction of propagation of light rays traveling through the atmosphere due to change in density of different layers of air is called atmospheric refraction. This is the definition. Why there is a change in density? As I explained, the temperature of the atmosphere is not constant, and which makes the change in density of the atmosphere. Not only the mass density, even the optical density also changes. And therefore, whenever light travels through the atmosphere, the direction of propagation of the light rays will continuously change. That means it undergoes continuously the refraction. So bending of a ray of light when it passes through the atmosphere due to change in its density of different layers is called atmospheric refraction. What are the natural phenomena? These are the natural phenomena that can be explained. Note here one important note, the same which I explained earlier. The physical conditions of the Earth's atmosphere are not stationary, not fixed. The hotter air is lighter, less dense than the cooler air which is above the hotter air, and has a refractive index slightly less than that of the cooler air. That means for a hot air, refractive index is lesser. For cold air, refractive index is more. But generally what happens, the hot air tries to goes up, and which will be replaced by a cold air. And therefore, if you look at the refractive index increases from top to bottom. So with this we will see the next. Here, apparent star position. Very quickly, you can see this diagram over here. At the horizon or near the horizon means something like this. What is the horizon? It is a line where the sky appears to meet the earth's surface. So near the horizon means at a slant angle. This is what you can see. See, at a horizon, when you look at the stars, the actual position and the apparent position are different. That means here this is the actual position, but the position of the star appears to be over here, and therefore this is the apparent position, whereas this is the actual position. And this apparent star position, which is slightly above or higher than the actual position of the star, is due to atmospheric refraction of starlight. First point. Now let us see why this happens so. Here also you can see the refractive index increases towards the earth's surface. That's a different issue, you should know that. Here also it is given, as you go above the earth in the atmosphere, Ri decreases. When you come towards the earth through the atmosphere, Ri increases. So let us try to explain why this apparent position is observed slightly above or higher compared to the actual position of the star. Let's see this. Apparent star position. First of all, it is due to atmospheric refraction of starlight. Now, why this atmospheric refraction takes place is explained in these paragraphs, and also because of the refraction, star's position is slightly above. The apparent position is shifted from the actual position. The temperature and density of different layers of atmosphere keeps varying, and hence refractive index changes gradually. Meaning, the refractive index of the atmosphere gradually changes due to change in density and temperature of different layers of the atmosphere, which is not fixed. Therefore, when the starlight enters the Earth's atmosphere, it undergoes refraction continuously. Since the atmosphere bends the starlights towards the normal, the apparent position of the star is slightly different from its actual position. Mark this keyword. Mark this keyword. See, why the apparent position of the star is different from actual position? As the atmosphere bends the starlight towards the normal, the apparent position of the star is slightly different from its actual position. Here, see here, all this is the atmosphere. The rays should have come straight over here into the eyes, but it will not happen. When the rays come over here, it will bend like this, and project it backwards, you will get the position of the star. And therefore, since the atmosphere bends the starlight towards the normal, the apparent position of the star is different from its actual position, and the star appears to be slightly higher or above the actual position of the star when viewed near the horizon. Slightly above the horizon when we view the stars, this is what it appears. So this is how we can explain the apparent position of the star. Next we will go to, here in this diagram also it is very clear. See, this is the here a boy is standing. These dotted particles indicate the atmosphere. This is the actual position of the star. When a ray of light enters into the atmosphere, due to atmospheric refraction, it bends towards the normal. When you project backward this bent ray, you get the position of the star, but this is the apparent position. And this appears to be slightly higher than the actual position or above the actual position. And this is how the apparent position of the star is different from the actual position of the star. I hope this is very clear for you. लेकिन जो भी मार्क किया हूँ इसमें these bullets, all these bullets should be covered in order to explain the apparent position of the star. Okay. Next, twinkling of the stars. Why do stars twinkle? Here, couple of 2 points are important, which I will highlight at the end of the expression. So let us read this. Why the twinkling of the stars takes place, or why do stars twinkle and why don't the planets twinkle? These two questions we will answer now. This is also due to atmospheric refraction. First of all, twinkling of stars, it is also due to atmospheric refraction. Distant stars act like point source of light. Point source means a light source is considered to be a point and the light travels in all direction. What is the extended source of light? Extended source of light is considered to be collection of all point sources. Simple example I will give you. One LED bulb can be considered to be a point source of light, whereas LED tube light, 2 feet LED tube light is considered to be an extended source of light, which is the collection of point sources of light. That is a simple way of putting it to explain what is a point source and what is the extended source of light. So distant stars, even though stars are very big, the distant stars act like point source of light. As the beam of starlight keeps deviating from its path, the apparent position of the stars keep on changing. Even the apparent position of the star is not constant. Why, you know? See, due to atmospheric refraction, when a beam of starlight enters into the atmosphere, due to atmospheric refraction, its path continuously deviates. Its path continuously deviates, and therefore even the apparent position of the star keeps on slightly changing. Therefore, the amount of light that enters into our eyes flickers, meaning varies. That gives twinkling effect of stars. When the quantity or the amount of light that enters into our eyes changes, that leads to the twinkling effect. That leads to that gives the twinkling effect, isn't it? And therefore, here hence the amount of light entering our eyes flickers, means fluctuates or varies also, we can say. Sometimes very bright and sometimes faint, and this leads to the twinkling effect of star. All these points are very important. While writing the answer, you collectively club together all these bullets. That gives a good explanation. So let us read once again. The 2 points are, which I said I would like to highlight. Starlight acts like a point source of light, and when it's and the amount of light entering our eyes flickers. These are the 2 key points, phrases. We should never forget this. So let us try to explain once again. The twinkling of the stars is due to atmospheric refraction. When a starlight enters into the atmosphere, its path continuously deviates, and because of which the apparent position also continuously changes, and hence the amount of light that enters into our eyes fluctuates or flickers, and sometimes very bright light, sometimes very faint light, and therefore this leads to the twinkling effect of stars. This is what you can write the explanation. Why don't planets twinkle? Important. The planets are much closer to Earth's surface, Earth's atmosphere, Earth, and are thus seen as extended sources of light. Planets are considered to be extended sources of light, meaning collection of point sources of light. In that case, what happens? Let us see the textbook explanation. Very important. How the textbook has written is most important over here. If we consider planet as a collection of large number of point-sized sources of light, then the total variation in the amount of light entering our eyes from all the individual point-sized sources will average out to 0. What averages out to 0? The total variation. The variation in amount of light enters, the variation in the amount of light that enters our eyes, that averages out to 0 because the extended source of light is a collection of point-sized sources of light. Do you understand? Therefore, if we consider planet as a collection of large number of point-sized sources of light, then the total variation in the amount of light entering our eyes from all these point-sized sources of light averages out to 0 and thereby nullifying the twinkling effect. Hence the planets do not twinkle. A simple answer. So these are the 2 points one must note down, and see here, all these you can club together in order to form a web of sentences, a paragraph you can make it. Okay, so this is how we can explain twinkling of the stars and why don't planets twinkle based on the atmospheric refraction and the quantity and the amount of light that enters into our eyes. Okay, so let's see next one. Yeah, here there is a question and would like to see how the topper is answered. What is atmospheric refraction? Use this phenomenon to explain natural events such as twinkling of stars, advanced sunrise and delayed sunset. First we will see the twinkling of stars, how he has answered. This is the diagram, apparent position of the star and actual position. Instead of original you can write actual position of star also. And twinkling of stars. The sunlight on entering the atmosphere undergoes refraction completely and continuously. It bends always towards the normal. Since the atmosphere is not stationary, the apparent position of the star changes. It appears slightly higher up. The amount of starlight that enters the eye fluctuates, so the star flickers and causes the twinkling effect. So the star appears to be twinkling, and this is because of the atmospheric refraction. Okay, some of the keywords, phrases, whichever I discussed that I had taken from the textbook are present, but I am sure my students would be able to write pretty much better than this explanation. Why do stars why do the twinkling of the stars takes place? First of all, twinkling of the stars is due to atmospheric refraction, and star can be considered to be a distant stars can be considered to be a point source of light. Whenever the starlight enters into our atmosphere, due to continuously changing atmospheric conditions, starlight undergoes continuous refraction, and the apparent position of star appears to be changing continuously, and the amount of light that enters into our eyes fluctuates, sometimes bright, sometimes faint. That gives to the twinkling effect of the star. This is what you can write, something like this. Probably you should be able in a position to write explain in a much better way. See, this requires a little explanation. Make sure that you use the keywords whichever we discussed. Fine students, let's go to the next slide now. Advanced sunrise and delayed sunset. See, here only 2 points we'll understand. Advanced sunrise and delayed sunset. It is due to atmospheric refraction. First point. Second, what is this? What is that it happens? Here you can see. Here, Earth here. This is Earth's atmosphere, and here this is the horizon. You can see this is a horizon. What is this horizon? Basically, a line where the sky appears to meet Earth's surface. When you see from here, the surface of the Earth and the sky appears to meet at this straight line, horizontal line. So at the horizon during sunrise, this is the actual sun's position. But when a ray enters into our atmosphere, it bends towards the normal, project it backwards, and sun appears to be over here. This is the actual position of the sun during sunrise, whereas this is the apparent position of the sun during sunrise. What is the actual sunrise? Actual sunrise refers to crossing of the horizon, actual crossing of the horizon by the sun is called actual sunrise. Once again, what is actual sunrise? Actual crossing of the horizon by the sun is called actual sunrise. But here, has the sun crossed the horizon? No. Actual sunrise has not taken place. But already sunrise has taken place due to apparent position of the sun over here. We see the sun over here. And this is due to atmospheric refraction. That means apparent position of the sun is advanced sunrise. Is it not advanced sunrise? Sun has not crossed, but still sun appears to has crossed the horizon, and therefore this is advanced sunrise. What is the time delay between the actual sunrise? What is the time delay of crossing the actual sun, the horizon? That is about 2 minutes. After 2 minutes, the sun will actually cross the horizon. So this is the advanced sunrise over here. What is advanced sunrise? Once again, sun has not crossed the horizon, but still it appears to have already crossed the horizon, and that is the position of that sun in that case is apparent position, not the actual position, and therefore sunrise has not taken place, but for us, the observer over here, the sunrise has already taken place. That is the advanced sunrise. Let us read this paragraph. Let us read a couple of photographs, and then once again I will explain that phenomenon, this advanced sunrise and delayed sunrise on the board, so that you will ever remember that. Fine. This is also due to atmospheric refraction. Because of this, sun is visible 2 minutes earlier than the actual sunrise and 2 minutes after the actual sunset. Understood? 2 minutes earlier sun is visible 2 minutes earlier than the actual sunrise, and sun is visible 2 minutes after the actual sunset. By actual sunrise we mean that actual crossing of the horizon by the sun. This is important to be noted. The time difference between the actual sunset and the apparent sunset, or the actual sunrise and the apparent sunrise, is about 2 minutes. The apparent flattening of the sun's disk at the sunrise and sunset is also due to the same phenomenon, that is atmospheric refraction. Apparent flattening means the sun appears to be a flat disk, circular disk, and that is called the apparent flattening of the sun's disk. That is also due to atmospheric refraction. Now let's see here, next slide. Here this is the Kanyakumari photo here. This is the sunrise, and here this is a sunset. In the morning you can see already sunrise has taken place here. No, sun has not crossed the horizon. Here this is a horizon, the sky meeting the earth's surface. Here, this is the horizon. Sun appears to be over here during morning. Sunrise has taken place already. No, sun is still below here, somewhere here, but for us already sunrise has taken place. This is due to atmospheric refraction, and it is advanced sunrise. The sun that we are seeing over here, it is not actual sun, it is apparent sun. Are I samajhe? Whereas sun is below here, he has not yet crossed, and therefore advanced sunrise. Here sun is setting here, isn't it? But already sun has set. Sun is here in this position. If you look at the horizon, now we are seeing the sunset here. See here, all these are evening lights here, and therefore this is sunset. And here sun's position is above the horizon, but already sunset has taken place. The sun is below here, but due to refraction, sun is appearing at this position, meaning there is a delay in sunset. Already sun has set, but still for us sunset has not taken place, means sunset is getting delayed, and therefore advanced sunrise and delayed sunset by 2 minutes compared to the actual sunrise and actual sunset is due to atmospheric refraction. Now I will try to explain this on the board once again, and then we will get back to the PPT. See, this is Earth. I have drawn one line called horizon and draw the Earth's atmosphere. Below the horizon, two suns are drawn here. This side sunset, this side sunrise. Let us start from the sunrise, and this is the atmosphere which I have written, earth and atmosphere, and this side sunrise, this side sunset. In the early morning, actual position of the sun is here, but advanced sunrise takes place, meaning even though the sun is here, the rays will pass like this, or let me show something like this. Yeah, it is better to show this way. Okay, you can do that. The rays are passing like this. When it comes over here, atmosphere, it is bending towards the normal, and here the observer is here. You produce backwards this one, and therefore the sun appears to be over here. Here, this is on the same straight line. Okay, remember, this is on the same straight line. Now the light rays are coming like this. When it enters into the atmosphere, it bends, and here this is the eye position, and as these rays enter, project them backward, therefore sun is appearing over here. Even though sun has not crossed the horizon, for us he has already crossed, the sun has already crossed, and the position of the sun is here. Therefore advanced sunrise is what we see. This is the actual position, actual position of the sun, and this is apparent position of the sun. APP, what is the spelling apparent? APP ARENT, apparent position of sun, which is advanced. Is it clear? Advanced. Now the time delay is 2 minutes, or whatever that is, the time delay or the time advanced is time difference. I'll write, that is the best. Instead of delay, I'll write the time difference is 2 minutes. Okay, now come to the sunset. Sun has already crossed the horizon in the evening. Sun's position is over here. Even though sunset has taken place, are we seeing actually the sunset? Let us see. Actual position of the sun during sunset is here, but this is how the rays pass. It bends towards the normal, this is the position of the eye here, observer. The rays are coming like this and entering into our atmosphere. It bends towards the normal and enters into the observer side, and therefore project it backwards, and along this horizontal line here there is a sun. See here, this both are this on the horizon, on the same line here, on the same line. So actual position of the sun here, that means sunset has taken place. But for us, the sun appears to be above the horizon, means we are seeing the rays of the sunlight, and therefore even though sunset has taken place, we do not see the sunset, meaning sunset is getting delayed compared to the actual sunset. This is due to atmospheric refraction, and this position of the sun is apparent position. Apparent position, where it is delayed sunset. Delayed sunset. That means the apparent position is delayed here. Apparent position is delayed, actual position already over here. So this is how you can explain the advanced sunrise and delayed sunset using the diagrams. How to draw the diagram? Draw Earth, atmosphere, one line that represents horizon and this represents atmosphere. Two suns you draw. One sun here, actual sun during sunrise and actual sun during sunset. Take a ray, bend it, project it forward and you can get the position of the sun, which is apparent position. During sunrise it is advanced, during sunset it is delayed. So the diagram also, I think it is very simple how to draw this one. Okay, so let us get back to once again the PPT now. So this is how we learnt about advanced sunrise and delayed sunset. This is how the topper writes. Pause the video and make a note of this one, and this is the diagram. Part 3 also will complete it. Scattering of light. Under the scattering of light there are three phenomena. Tyndall effect, why the color of the sky is blue, and color of the sunrise and sunset. These three things we'll see. So what is the scattering of light? What is the Tyndall effect? We'll see first. What is Tyndall effect? Earth's atmosphere is a heterogeneous mixture of minute particles such as smoke particles, tiny water droplets, suspended particles of dust and molecules of air. This is how the Earth's atmosphere is a heterogeneous mixture. So when a beam of light strikes or enters into the atmosphere consisting of such fine particles, the path of the beam becomes visible, and that phenomenon is called the Tyndall effect. I hope this is very clear to you. The Tyndall effect is observed when a fine beam of sunlight enters a smoke-filled room through a small hole, and also when sunlight passes through a canopy of dense forest. These are additional 2 points. Where do we observe the Tyndall effect? In atmosphere. These are the two examples. Now, the color of the scattered light depends upon the size of scattering particles. See, important is the color of the scattered light depends upon the size of the scattering particle, meaning, just remember one point, finer particles would be able to scatter different colors by different intensity. Larger particles would scatter all the colors equally. I hope you are able to understand this. Means finer particles would be able to scatter different colors by different intensities, whereas large sized particles will scatter all the colors by equal magnitude. Keep these 2 points in mind. So let's go to the next this thing. One more important property you should know, how the amount of scattering is dependent upon the wavelength of a particular color. Intensity of scattering is inversely proportional to 4th power of lambda, where lambda represents wavelength. Meaning, intensity of scattering is inversely proportional to the wavelength. More the wavelength, lesser is the intensity of scattering. Lesser the wavelength, more is the intensity of scattering. For red, we have more wavelength, approximately 750 nanometer. For blue, approximately 400 nanometer. So, red light has more lambda, less intensity of scattering. Red light having more wavelength is scattered least. Blue light having lesser wavelength, around 400 nanometer, is scattered most. So, if you compare the red versus blue light, scattering effect by the smaller particles of the atmosphere, the intensity of the scattering, if we look at, red is having larger lambda, that therefore it is scattered least. All shorter wavelength colors are scattered most. Longer wavelength colors are scattered least because of the relation, inverse relation between intensity of scattering and lambda. So that is what it is explained over here. According to Rayleigh, the amount of scattering or intensity of scattering is inversely proportional to the 4th power of the wavelength. Therefore, light of shorter wavelength is scattered most and the light of longer wavelength is scattered least. There is no change in the wavelength of the light rays during scattering. the scattering will not affect the wavelength, that you should remember. The most beautiful phenomenon such as blue color of sky, white color of clouds and red color of sun during sunrise and sunset are explained by the scattering of light. Why the color of the sky appears blue? See here, the red light has wavelength of about 1.8 times greater than the blue light. This is given in your textbook. That means the red light has nearly 2 times the wavelength of the blue light. Therefore, blue color has shorter wavelength than red. Thus, sunlight passes through when the sunlight passes through the atmosphere, fine particles in the atmosphere or in the air scatter the blue color, which is shorter wavelength, more strongly than the red color. The fine particles of the atmosphere will scatter the shorter wavelength colors more strongly, such as blue color compared to the red color. The scattered blue light enters our eyes and hence the sky appears blue. That's what it is. Next, on the surface of the moon, important, why the sky of the moon appears dark is the question. On the surface of the moon there is no atmosphere and therefore there is no scattering effect, and hence the sky of the moon appears to be dark. If there is an atmosphere, then you can find the scattering. If there is a thin atmosphere or if there is no atmosphere, scattering is not observed and the sky appears to be dark. What about the white color of the clouds? It consists of larger particles such as water droplets, which will scatter all colors by equal amount, and hence net scattering effect is nullified, and therefore the colors of the cloud appear to be white. So let us see here. Large particles like raindrops, dust or ice particles present in the atmosphere scatter all the wavelengths of the light almost equally. Hence the clouds which have droplets of water scatter all colors by equal magnitude, giving the white appearance. So the clouds generally appear white. So these are the explanations for blue color of the sky and white color of the clouds. Make a note of this. Next, color of the sun at sunrise and sunset. So there is a small experiment over here, probably in my Walter Levin's one video lecture link I had sent. There also he explained all these phenomenon. Of course, the textbook explanation and his explanation are same with respect to the chemicals taken in this. So let us see this one. This will help us to understand the color of the sun at sunset and sunrise, during sunrise and sunset. See here, activity. Place a strong source of white light at the focus of the converging lens L1. S is the source of light, L1 is the converging lens, L2 is also converging lens. This is a screen over here, and this is a cardboard with a hole here. This is a beaker containing water. And what is that we are going to see here? Here this point source is considered to be a sun, and when we view from this side, here it is a eye. Screen is nothing but the eye here, and here also one more eye. Observer can be here and observer can be here also. So let us see what happens to the observer when these beam of rays pass through a beaker containing water, and if we add some particular chemical, what happens? We'll see that. Place a strong source S of white light at the focus of the converging lens L1. The lens provides a parallel beam of light. Allow the light beam to pass through the transparent glass tank T containing clear water. Allow the beam of light to pass through a circular hole C made in a cardboard. Obtain a sharp image of the circular hole on the screen. Here, sharp image of the screen. Okay. Now, what we will do is dissolve about 200 grams of sodium thiosulfate or hyposulfate in the about 2 liter of clean water taken in the tank. Add about 1 to 2 ml of concentrated sulfuric acid to the water. What do you observe? You add sodium thiosulfate about 200 grams and 2 liters of clean water taken in the tank, and add about 1 to 2 ml of concentrated sulfuric acid to the water. What do you observe? Let us see. You will find the microscopic sulfur particles precipitating because of the sodium thiosulfate and because of the sulfuric acid, and because of the reaction between the two, fine sulfur particles are precipitated inside, in about 2 to 3 minutes. As the sulfur particles begin to form, you can observe the blue light coming from 3 sides of the glass tank. Here 3 sides means all around this glass the blue light starts coming out. You cannot see any red light. This is due to scattering of short wavelengths by minute colloidal sulfur particles. Observe the color of the transmitted light from the 4th side of the glass. This side, or you can say front, back, top, bottom, all around like this, the blue light is appearing, whereas on this, the orange or the red color is appearing. It is interesting to observe at first the orange red color and then the bright crimson red color on the screen. See, let me explain over here. In this, water is taken, clear water, add sodium thiosulfate and sulfuric acid. The reaction between the sodium thiosulfate and sulfuric acid gives rise to the precipitation of sulfur particles. The sulfur particles in this water tank will behave like colloidal particles, so it becomes a colloidal solution. So colloidal solution will exhibit Tyndall effect. Not only that, it gives scattering, it leads to a scattering effect of the light. So the white light, source of white light here, it consists of all the colors, but blue color having shorter wavelengths is scattered in all directions. So here, so if I see from this side, I see the color of the water to be blue here. But the person who is standing over here, for him the blue color is scattered away, whereas red color passes straight, and therefore the observer over here sees the red color of the light over here. That means for him it appears to be a red color. For him who is standing over here, the light entering into here, his or her eyes will be blue color. Why it is so? Blue is scattered over here, red is not scattered, red passes straight, and therefore you find here the red crimson color image of the source of light on this screen, whereas you can see the blue color over here. So this is due to atmospheric scattering, and exactly the same thing happens during the sunrise and sunset, which we'll see in my next slide. See here, during sunrise, this is the earth, atmosphere, observer is here. During sunrise, sun rays travel a larger distance through the atmosphere from here to here, larger distance through the atmosphere. Once the sun comes in the noon, then check this distance. The distance traveled by the sunlight through the atmosphere is quite small compared to the sunlight traveled through the atmosphere during the sunrise. So during sunrise, what happens? During the sun, when the sun is overhead, what happens? We'll see now. At sunset or sunrise, the sun looks almost reddish. This paragraph explains. The sun rays have to travel a larger atmospheric distance. You can see from here to here. As the wavelength of the blue is less than the wavelength of the red, most of the blue light and shorter wavelengths are removed by scattering. From here to here, blue light goes up and down, red travels straight. Only red color, which is least scattered, is received by our eye and appears to come from the sun. Hence the appearance of the sun at the sunset or sunrise and during the full moon near the horizon may look almost reddish. Here the sun rays are entering the atmosphere from here to here. They travel longer distance. The finer particles of this atmosphere will scatter away the blue light. Blue light goes this way, red light travels straight, reaches the observer, giving the appearance of the sun to be reddish in nature. When the sun comes over here, in that case, this is the distance traveled by the sun ray through the atmosphere. That means at noon, sun appears white. Why it is so? At noon, the sun is overhead and sunlight would travel shorter distance relatively through the atmosphere. Check this one, only this much is the distance. Hence at noon, the sun appear white because only little of the blue and violet colors are scattered. This side and this side, only little quantity of blue light is scattered, but most blue also travel straight. All the colors put together give rise to the white appearance, and therefore during noon the sun when the sun is overhead, the sun appears to be white because there is no scattering effect of any color at all. So this is how during sunrise and sunset the color of the sun appears to be reddish. During noon the color of the sun appears to be white. And next is the red color of traffic signals. Wavelength of red color is longer, will not be scattered, and hence it is visible from the far distance. Hence the color of the traffic light is red. It travels through larger distances because atmospheric particles, fine particles or whatever, those will not be able to scatter red light because of its larger wavelength, and hence these red colored light can travel far distance, and hence we use this as a stop signal, especially in traffic signals. Okay, so this is how the chapter, I think the chapter ends. Let us see what else. Yeah, we have completed this chapter. Whatever the portions was there for you, that has been completed in all respects. I request you to pause the video and make a note of everything. Go through several times, then only you will be able to understand this, all these natural phenomena, and what is the natural phenomena and which natural phenomena explains those phenomena. These are the things to be studied properly, and you have to remember also. So in my next lecture, I will be taking question answers pertaining to the colorful world, and there it completes in all respects. So let us end the lecture over here and see the next lecture. Thank you for watching.